Yeah, I hope we are recording now. Yes, I think we are recording now. Fine. Jesus. Fine. So let me share my screen. Uh, okay. Is the screen visible? I think. Please one. Thank you. Thank you. Thank you. Thank you. I see. Yes. All right. So now let us start. All right. So as always, let me start with a quick introduction. So this course is analog. This course is analog VLSI design. It's an NPTEL course. And the instructor for this course is Dr. Iman Mandal. He is an assistant professor in electrical engineering department at IIT Kanpur. Uh, my name is Mayank Anupam. I will be holding these tutorial sessions or discussion sessions. I am a PhD student in the electrical engineering department at IIT Kanpur. All right, so that concludes the introduction. Let us now start. So today we will be discussing the content that was covered in week 2. All right. Uh, the overview of the discussion was overview of uh, the broad topics covered in the week two content was non-linearity, right? How do you handle non-linear elements? That was the broad agenda of about what was covered in week two. So uh, the first thing that was covered was to, if you are given a general non-linear element, how do you go about analyzing it, right? What kind of analysis do you do to handle a non-linear element in general? How do you look at it? So that was the first thing. Now, once you get an idea of how to handle non-linear element, once you have a general idea of how to handle a non-linear element, then you go ahead and try the tricks that you learned to handle non-linear elements on some of the common electrical electrical elements that you have, right? That you did next. Now after that, we were more we went we went since our end target will be a MOSFET, so we are kind of focusing on that. So at as the last part of this of to conclude this week two, the instructor introduced you to a general two-port non-linear network, right? And from here on, you will see that from here on he will introduce MOSFETs and all everything. So anyway, uh, first of all, let me ask you: did you have any problem in understanding the content that was covered in week two? I mean, I will only go into those topics which you felt difficulty in understanding. Otherwise, I will skip these things. Uh, is anyone here? I mean, does anyone have any doubt? Okay, Nikhil says he's fine with everything. So anyone else? If you have any doubt, you can ask me now. All right. So let me also quickly check the discussion on the forum. Okay. I guess that is where people have asked a lot of questions. So today I'll be starting with this only. I'll start with the forum only. Okay. So okay, there was a question in the forum which I saw earlier. There was a question in the forum about so in week one we saw that a non-linear element is required. So we Hmm. So one question was about the use of non-linearity. I mean, we know that non-linearity is required to have power amplification, right? In the network. So there was a question by someone who asked that in a particular example which sir explained, there was a network. Okay, there was this signal source. This is VS. Then there was another signal source here, and then there was this network. It's a non-linear. It's a linear network, LTI. Okay, this is an LTI network, and let's say it was powered by some DC source, and then there was this RL. And so the question was that ultimately when we will see at the output V out, we will see that there will be a DC because of this VDC, there will be a DC power. Okay, I see some queries in the comment section. All right, so I will definitely solve problems today. Okay, this is just because I saw a question in the discussion forum. That is why I'm covering this. So after that, I will be going on to the problem solving only. Anyway, so we saw that because of VDC, there will be a DC power. Okay, and this signal Vs source, this will come out at V out. This its power will also come onto the V out with some factor alpha, right? So there will be some signal power. Okay. Now at the output V output, what will you see? You will see some DC power due to VDC plus some signal power due to Vs. Okay. Now, the problem was that you wanted power amplification, isn't it? But you end up seeing here that the power amplification, when you say power amplification, it means that you need the power of the signal to be amplified. Okay. Here, what is happening? There is some signal power, and on that you are simply adding a power which does not have any signal information in it, isn't it? Here, the signal power was different, and at the output in LTI case, in case of an LTI network, this at the output you have two different powers, right? One is DC power, which is because of this DC source, and one is because of this source, the signal source. You have some signal power here, okay? And the final objective was that we want to somehow use this DC power, this power which is supplied by a battery, okay, and somehow use this power to amplify my power in the signal that is coming at the output. But that is not possible here. As you can see, there was a because DC power is you will see two separate powers. There will be a DC power, and then there will be a signal which will be standing on it. Okay, so overall, if you see, you will observe that you do not have any extra power in the signal. Hmm. Whatever power you are getting due to the this DC source, this is simply appearing as it is at DC itself. There's no frequency translation. I hope that clears. So this was a doubt, so I thought might cover it. Anyway, so if there is no queries in this in these topics which was covered in week 2, so I'll just go on to solving the questions. Okay. So today I have only one question. I think this will cover most of the problems which you'll face. So this is very similar to what problem number 3 in this week's assignment also. Okay, so I hope you will be able to understand this. If you understand this, you will be able to solve all the other questions that are there. Okay, fine. So the question here is that you have a new kind of element. Okay, you have discovered a new element in your lab, and the element is this. Okay, there are two terminals for this element. This is one. This is second terminal. Okay, and if you define that the positive terminal of the element is this one and the negative is this one, then you have positive to negative voltage drop, which is Vn, and the current flowing from positive terminal to the negative terminal in this fashion, that is In. Okay, and between In and Vn you have a relationship which is given by this particular graph. Okay, let's say that your current and voltage relationship is only defined till this point. I mean, when the current is less than 9, so this is by the way in milliamps. Okay, and this is in volts. So let's say your current and voltage relationship is only confined between these maxima. Okay, so let's say your current and voltage relationship is only defined in this area. So this is the current relationship, voltage to current relationship which you have in this for this particular element. Okay, now this here are the following questions. This element you are using it in this fashion. Okay, there is a current source here. All right, and this current source, and then there is a resistor Rs. This Rs is a simple normal resistor. Okay, and you have also used that element here. Now the questions are the following: is the element E linear or non-linear? First question. What do you think? Is the element E linear or non-linear? So I mean, guys, you guys can maybe unmute yourself if you want to say something. I mean, it's very
No,
difficult
no,
for me to keep checking the comment section.
no, non-linear, sir.
Okay, non-linear. So why do you say that? Why do you say it is non-linear? Uh, Subara, I guess you answered, right? So why do you
Yes,
say
yes.
it is non-linear?
Uh, because the relation between Vn and In is not linear, sir.
Yeah, so how? Okay. So tell me, how do you define linear relationship between two elements? What kind of a graph it should have been for linear relationship?
A standard graph.
Come again? I didn't understand.
Standard graph.
What is meant by standard graph? See, I am trying to understand what you understood. Okay, so please help me understand. What do you mean by standard graph? So how will the relationship here look like? Okay, let me ask you this way.
Y is equal to mx. It should be in the form of y is equal to mx.
Yes, it should be in the form of y is equal to mx. Correct. That is exactly correct. It should be in the form of y is equal to mx. Yes, that is the linear relationship. Okay. This kind of a relationship is called linear relationship. However, this graph doesn't look like that, right? It doesn't seem to follow that. It would have been linear if this would have been like this, isn't it? However, this kind of changes its nature this way and then does all weird things here. So it's non-linear. So that answers this question. It's non-linear.
As current increases, voltage is also changing.
So what? That also happens for resistor, right? Linear relationship means the uh, linear elements, they have to follow this kind of a relationship. Y is equal to mx, right? Or in other word, V is equal to some m times I. Okay. This relationship has to be followed. Only then can you say that it is a linear element. Okay. Fine. Now comes the question. If Rs is equal to 2 kilo ohms, okay, this element here, it is 2 kilo ohms, and then find the voltage across and the current through each of the elements in the above circuit to get a current of 6.5 milliampere in the element E. So tell me, how should I proceed? I want a current of this IN, sorry, this IN here should be how much? 6.5 milliamps, right? So for that you have to solve. If RS is given to you and this current is also known, the current flowing through this element, find out what is the current that will be flowing through each of the elements, which means that this IA, okay, this current source, how much current will it be supplying, how much current is flowing through RS, and what will be the voltage across this element. All those things we want to know. So help me, how do you proceed with this question? How to solve this question? So if you help me finish this question first, I will also cover two questions which I wanted to discuss last week. So quickly help me. So first of all, we know what is the current that is going to flow through this element, right? So first thing that we need to do is we need to find out that this current corresponds to what voltage, right, in the element. So as you can see it here, that 6.5 milliampere will be somewhere here, correct? It is 6.5 milliamperes current. So how much voltage should it correspond to?
3.5.
Correct? 3.5, isn't it? Sorry, it is 3.5 volts. Okay. So one thing is sure that to get this current 6.5 milliampere to flow in this element, you need how much voltage? This Vn has to be 6.5 volts, right?
3.5.
Oh, sorry, yeah, 3.5. 3.5 volts for In is equal to 6.5 milliamperes. So that is known to you now. Okay. Now when you know that the current voltage here is 6.5 volts, sorry, 3.5 volts, what is the current that is going to come out of this resistor? That is going to flow through this resistor RS. So what will be IRS? It will be 6.5 milliampere, sorry, 3.5 volts divided by RS, right? Which will be how much? 3.5 volt divided by 2 kilo ohms. How much will this be?
1.75 milliamps.
Yeah, 1.75 milliampere, right? Now tell me how much current this is supplying. IA is equal to, one guy has said IA is equal to 8.25. Is that correct?
Yes.
Yeah. So looks like it is correct. So basically IA will be how much? IA here will be 1.75 milliamps plus 6.5 milliamps, which will be 1.8, how much? Sorry, 8.5
8.25
to
milliamps.
5 milliamps. Correct. Okay. So that was easy. That was very easy. No problem there. So this also is done. So the current is 8.25 milliamps in IA. Correct. Voltage is 3.5 volts. That is fine. No issues. Now, what is the power consumed by E? What is the power dissipated in E? I mean, that is the question. What is the power consumed or dissipated in E? I think I covered this thing last week also. How do you calculate power dissipated in an element?
V into I.
V into I, is that it? I mean, was there a catch in it? It will be V into I, correct, but there was a slight catch in this statement. This I cleared last time. You can only say that power dissipated is V into I when you follow a certain convention, okay, which is called passive sign convention. According to passive sign convention, if you are naming if you are putting the signs for the elements, only then can you say that the power dissipated is V into I. Okay. So since here anyway we have used passive sign convention, isn't it? We have used this as plus, this is minus. Once you define that what is plus and what is minus, then you have to also say that then the current which will be entering the plus side will be considered positive, isn't it? That was the that is the passive sign convention which we are going to follow. All right. So here what is the what will be the sign of the current, positive or negative? We have found out IN is 6.5 milliampere, correct? So is it entering or leaving this node? What is it doing? IN here, is it entering this particular plus terminal or is it leaving?
Entering.
Entering, right? So IN here will be what? Positive, okay? IN will be taken positive. So positive 6.5 milliamps. Let me draw it somewhere else. Okay. So we have this element and sorry. So this was your Vn. You defined Vn, okay? Like this. Now, after all the calculations, you saw that the current IN is coming to be it is flowing in this direction, right? After all the calculations, you saw that the current IN is flowing in this particular direction. Okay, so Vn was how much? Vn was 3.5 volts. IN was plus 6.5 milliamps. So what is power dissipated? Since this is already in passive sign convention, so what will be the power dissipated?
22.75 milliwatts.
Yeah, so it will be Vn times In. Okay, it will be how much? So whatever it is, 3.5 into 6.5 milliwatts, correct? So just calculate it, whatever it is, it will be. So that also was easy, no doubts there. So did anyone have any doubt here? What we did, we used passive sign convention, okay? Power dissipated is not minus, okay? Here in this case it will be positive. I am talking about power dissipated in E, okay? It will be positive here because the according to passive sign convention, the voltage terminal here, once we define what is positive and negative for a term for an element, after that we have to see what is the direction of current, okay? The current direction will be taken as positive when it is entering the positive terminal and leaving the negative terminal, okay? That will be taken as positive. And power dissipated in any element according to passive sign convention is how much? Power dissipated is V times I, okay, in any element according to passive sign convention. So here everything was according to passive sign convention, that is why it is dissipating power. Okay, that is okay. Now let us ask another question. Okay, so this is also clear, no doubts here. Yeah, this is interesting. Now let's say your current IA, this current source, okay, this current source IA is some IAQ plus some small plus some another small IA, where IA is a this guy 0.2 milliampere into sine of omega t. Find the net current through the element E. How do you solve this? Now this current source IA is how much? So earlier you calculated how much is the total current IA, right? Here 8.25 milliamperes. So this was what? Question number 1, 2, 3. This was question number 3. So now question number 4 you have IA is equal to 8.25 milliamps plus 0.2 milliamps into sine of omega t. Okay, this is the question. So find the net current through E. How do you solve this question? What do you do? Tell me, what do you do?
Because IA is combination of DC and AC signal. Uh,
Yes.
for AC signal, we know how much power is there. Uh,
So,
current, how much current we know.
yes.
We have to take the small signal equivalent of capital E element.
Yeah, so there are two ways, right? See, the thing is that um, one way to do this will be plain old way, right? Wherein what you will do, you will solve. Okay, you will start solving. So you have IA is equal to whatever you are given IA here, correct? So because of this IA, you will solve the KVL, KCL, whatever. Okay, let's say the voltage you here you assume as V0, okay, or let's call it VA only. No, it is VN. Excuse me. Yeah, so assume that the voltage here is Vn. Then you write KCL at Vn. So what will you have if you write KCL here? The current IA that is entering this node should be equal to all the currents that are leaving this node, right? So current IA will be equal to Vn over Rs, right? Plus what? Plus In, correct? That is what you will get, and then you will have to solve In is equal to Ia minus Vn over Rs. But the problem here is that you do not know what is Vn, right? But you know there is a for In and Vn you have a function given here, isn't it? So this will be slightly difficult to solve. In that, I mean, it is solvable, but it is slightly difficult to do. So what you do? You do the other thing that was explained to you by the instructor. So this is slightly difficult to do. Mm, So what do? You find the small signal equivalent. Okay. So how do you find the small signal equivalent of this particular element E? How do you do it? You can unmute yourself and say, how do you? What is your strategy to find the small signal model of this element? Yeah. Go ahead.
Sir, we need to find the slope.
Okay. Good point. Let's do that. Huh. So what do? You find the slope. So where do you find the slope? What do you mean by small signal? You want to basically linearize, right? In the vicinity of that bias point, isn't it? In the vicinity of this of the large of this quiescent value, in the vicinity of this quiescent value, you want to linearize the circuit, right? You want to linearize the overall network. You want to find out the linear model for this circuit. Since this because this is a non-linear element, that is why you are having trouble, right? So that is why you want to find the non-linear equivalent. Sorry, pardon me. So since this is a non-linear circuit, non-linear relationship, that is why you have difficulty in solving this equation like this, isn't it? Had it been a simple resistor, Had it been a simple resistor, then you didn't need to do all these small signal equivalent, right? You can simply find it right here. But since the relationship between IN and VN is not very straightforward, right? It is not a linear relationship. That is why you are having difficulty in solving this question, solving this equation. So that is why you want to what? You want to first find a linear relationship between IN and VN, right? You want to linearize the whole network, whole element of this IN versus VN relationship in the vicinity of a certain this thing quiescent point, right? And what is that quiescent point in this case? Where is that quiescent point in this case?
8.25 milliamps.
8.25 milliamps is the current that is flowing through here, right? But we already know that because of this current 8.25 milliamperes, what was the quiescent current that is flowing through this element E?
6.5.
Yes, already given here, right? So what do you want to do? You want to linearize your system in the vicinity of this, isn't it? This is where you want to linearize it. So tell me, what will be the slope in this section? What will be the slope here? What is the slope here? Basically what we are doing del Vn upon del In, correct? At what point? When In is equal to 6.5 milliamps. So what is that?
4.4 minus
Minus 1.
Okay, let's try that. So it is how much? 4 minus 3. So basically 3 minus 4. So V2 minus V1 divided by I2 minus I1. So I2 is 7 minus I1 is how much?
6.
Yeah, it is. Oh, it's my bad.
it may be
Let me
6.5 minus 5.5.
let's align it in the boxes so that it's easy to see. Yeah, good. So it is 3 minus 4. It is 3 minus 4 that is there minus divided 7 minus 6. So how
6.
much is that? Minus 1 divided by
Minus 1.
minus 1, right? Slope is how much?
Minus
Minus 1.
1.
Yes. So how does it look like in this case? So you see that del Vn by del In, which is what? Tell me. So what did you understand with this by this del In by del V1 Vn? This was Y parameter, right? It was a Y parameter, correct? Conductance rather. It was G. So it is a I over V, right? Current over voltage. It's what? Conductance. So what is voltage over current? What is this? Voltage over current?
Resistance.
Resistance. So let's call it some R. Let's call it R equivalent. Okay. But you see that R equivalent is how much? 1 kilo minus 1 kilo ohm, isn't it? You see it is minus 1 kilo ohm, isn't it? Is that understood?
Yes, sir.
So, I mean, do you have any doubts here? Like, how can the resistance be negative? Do you have a doubt here? How can the resistance is negative? How is the resistance negative here? Have you ever seen a negative resistance?
Sir, in nonlinear elements, it is possible.
Yeah, so that's what, yes. So this negative resistance here is not an actual physical resistance, okay? It's just that we have modeled it like this. We have found out what is the model of this element. But the element here in itself, it's not a negative element, negative resistance any element, right? It's an element which with all the characteristic as positive only. This element, you can see that all the characteristic here is in the first quadrant itself. So it's a positive, every quantity is positive here. However, this elements, when we did mathematical manipulation of this element, okay, element's characteristic, we wanted to find a small signal equivalent of this element. So there it can be negative, right? Because this is not a physical thing, it's just a mathematical manipulation, it's just a mathematical model. Okay, so here that is why we are seeing a negative value of resistance. So it's minus 1 kilo ohms. Okay, now that we have the this relation, this element here, now we can solve it. By the way, when you start doing small signal, so you have to do small signal for each and every element, isn't it? You found out what is the small signal of this element. So what is the small signal of this resistance element of this? What is the small signal model of this resistive element
Sa-
RS?
Same.
Same, yes, because it's a linear thing, right? So resistance relationship. Okay, let me write it here. First of all, the small signal equivalent of E is equal to a resistance, not resistance, let's call it like this. Its value is how much? R is equal to R equivalent is equal to minus 1 kilo ohm. So that concludes this one. Now, small signal equivalent of RS. So we know that for RS, the relationship is simple. It is a linear relationship. Correct. It's a straight line like this. So no, even if you linearize it somewhere, even if you find the slope somewhere, the slope is always the same, right? It doesn't change. So the slope will be how much? Slope will be RS only. So V del VRS upon del IRS. So that will again give you RS only. Okay. So this is not going to change. So small signal equivalent of RS is simple, the same resistance, no change. Okay. Now what is the small signal model of this current source?
Replace it with delta.
Small signal model IA is right. So what is the current IA actually? Current IA is this guy, right? So what is this? It's a 8.25 milliamps of constant value into plus 0.2 milliamps sine of omega t. Correct. This is what it is. All right. So first of all, tell me what will be the small signal equivalent of this current source.
0.2 milliamps sin omega t.
Yes. So this part here, since it is anyway constant, it is not going to change, right? I mean, even if you differentiate it with respect to voltage, it is not going to change. So this is simply going to be this is simply going to not come into effect. This effect is not going to come. Its effect is not going to come, right? So the small signal equivalent of this current source will be another current source like this, either like this. Uh, it will be small Ia, which will be equal to 0.2 milliamps into sine of omega t. Okay. So the now if you redraw the small signal equivalent circuit, what will you get? There will be a current IA. Okay. Then there will be a resistor like this, RS, sorry, resistance RS like this, and then there will be another element which has negative resistance, right? And this will be R equivalent which will equal to minus 1 kilo ohms. Correct? This is 2 kilo ohms. And IA we already know it is 0.2 milliamps sine of omega t. Correct? Okay. So tell me now what will be the current that is going to flow through this guy. What is the current that is going to flow through this guy? Anyone? What is the current that is going to flow through this guy?
IA into RS by RS plus R equivalent.
Yes. So first of all, let's find out. So this is a parallel current, right? Parallel resistance, a current division parallel this thing. So how it is? So I n, or rather small I n, is equal to IA into what? RS upon RS plus R equivalent. Correct? How much will this be? IA is 0. Or rather let it be IA itself. I into RS is 2 kilo ohms divided by 2 kilo ohms minus 1 kilo ohm. That will give me how much? IA into 2K or 2, right? So that will give me 0.4 milliamps sine of omega t, isn't it? 0.4 milliamps into sine of omega t. That is the current that is going to flow into this guy. Okay, good. Now tell me what will be the voltage here? What will be the voltage Vn here? Voltage Vn.
minus 0.4 sin omega t volts.
So this will be Vn times, sorry, In times R equivalent. So how much is In? In is 0.4 milliamps sine of omega t, and multiply this with how much? Rs, which is minus 1 kilo ohms. This will be 0.4 volts, isn't it? Into sine of omega t. Am I correct?
Sir, what about the minus sign, sir?
Oh,
What we
right.
have to
Correct. I forgot about it. Yeah. So this is a minus 0.4 volt sine omega t. Now tell me what is the average power dissipated, uh, or rather what is the power dissipated in this element, R equivalents. By the way, right now I'm talking about the signal power. Okay, so here also that the same point that I was trying to make. You see, you have given a DC current, okay, to your source, a DC current, and over that you have also given a AC current source, AC current. This AC current is basically the signal that you are trying to feed. You are giving a DC quiescent current, okay, and then over that you are also feeding to the system a signal current, okay. So now my question is, because of the DC current, you know what is the voltage and everything, right? You already calculated, we already calculated that here, everything we calculated. But now I am interested in the signal, this thing, signal characteristic. So signal you have given at input is 0.2 milliamperes into sine omega t. Signal frequency is sine of is omega, right? Signal frequency is omega. Now at the output, what is the signal power that you are getting? How much power is the how much signal power is being dissipated by this element? How much signal power is being dissipated by this element? Lakshmi, the RS value is not minus 1 kilo ohm. It is the R equivalent which is minus 1 kilo ohm. Okay, this guy. This R equivalent is the model, small signal model of this element. Okay, the small signal model of the element E. Right, that is what we found out. When we found out what is the small signal model of this element E around this quiescent point, that is when we found out what is the R equivalent here. Okay.
Sir, as it is a small signal equivalent, shall I use? Is it good to use R equivalent small r, or
Yeah, you can use that. I just
oh, okay,
wrote it here R equivalent. Okay, so you
oh,
can
okay, sir. Okay.
actually in any small signal parameter you have to use small signal only, small letters only, alphabets. Okay, so this was a mistake. Yeah, I shouldn't have used R equivalent like this. But anyway, fine. So tell me what will be the power dissipated in the element E. So here also we saw that the current IN, so we have assumed that in this element, R equivalent element, this is positive and this is negative. We have assumed that, okay? And we found out this, and when we assume the positive and negative terminal, then according to passive sign convention, we take this current, this current as positive, right? The current in this direction as positive. So here R equivalent, we already know what is the current like this, right? Current is already known to us, 0.4 milliampere into sine omega t. Okay, but the voltage here from between these two terminals, that is what we have found. What is Vn? Vn is equal to how much? Minus of 0.4 into sine of omega t. This is the voltage that we have found. Okay. Yeah. So this is the situation that we are in. In is equal to how much? 0.4 milliamps sine of omega t, and the voltage is minus 0.4 sine omega t. So what is the power dissipated? It is Vn into
IN.
In, right? So by the way, this is instantaneous power. Okay, this is the instantaneous power dissipation. So this will be a function of time. So how much will this be? Minus 0.4 into sine of omega t multiplied by 0.4 milliamps into sine of omega t. This is voltage. So this will be how much? Minus of 0.4
0.1 minus
into
0.1.
sine of omega t the whole square. Correct? So it is 0.16 sine square omega t. So this is the instantaneous power. Okay. Now, if you find out what is the average of this, you will see that the overall power will become negative, right? So here PD is negative. Correct. Even if you take the average, it will be negative. So what is happening here? I asked you what is the power dissipated by E, and the final answer that you are getting, final power dissipation value that you are getting is negative, right? What does that tell you about the element?
It's actually delivering the power.
Yes, it's actually delivering the power in the it's actually delivering the signal power, okay, not the DC power. DC power, it is still dissipating. If you look at the DC values, you saw that the voltage was 3.5 volt and the current was how much? 6.5 milliampere in this, right? So it is actually taking DC power, but somehow uh, converting that DC power into some AC signal power. Okay, it is actually supplying more signal power. Okay, it is actually not dissipating but supplying signal power.
Sir, it is order of milliwatts, I think, sir.
Yeah, it will be in milliwatts only.
It
So
milliamps into volts here. PD here. It is
yeah, it will be milliwatts only. Yes.
yes.
So good. So now that we are clear on this, so I think we have discussed everything in this. The interesting thing that was that I wanted to say was this only, that your power dissipated here is actually negative, which means that the element is actually delivering power. Another exercise which I would like you to do would be, so instead of 0.2 milliampere here, let's say the current was 0.6 milliamps. So the question would be, solve. So this is one. This is one. This is two. This is three, four, five. Now six. Solve for if IA is equal to 0.6 milliamps into sine of omega t. Okay, I would like you to do this on your own in the when you go back. Okay, just do it. I'll ask you. I will follow up on this in the next session. Okay, this is definitely something which I would like you to solve, which I would like you to try. Okay, so this I think concludes this question. Now let's go back to week one. Yes, Sakya Sinha, you have a doubt? You have raised your hand.
Yeah, so as you have completed the numericals, we have two kind of power is playing there, right? One is
Yes,
for DC and another is for AC.
yes.
So if there is a net power dissipation, it is asking, then we should calculate it, right? Our 3.5 volt into 6 point something
Yeah, it is
milliwatt
asking. Yeah, yeah.
minus this,
Correct,
right?
correct. Yes, yes. Net power dissipation means you have to find out the net voltage and the net current. Okay. When
Yeah,
you do
so
that, then you will
yes,
see that it is
okay.
actually dissipating. So there is no element other than the active sources, right? Other than not the active sources, but other than the independent voltage or current sources that you have in the circuit. Other than that, there will be no element which will be or rather, sorry, my mistake. Other than the independent or dependent sources in the circuit, you can never have power delivered by any other element. Okay, all these nonlinear elements, these all will be having a power dissipation only. Power, it will all dissipate power only. The
Okay.
easiest way to understand whether an element will be dissipating net power or will it be delivering net power is to check its voltage to current relationship. If the VI relationship is in the first or the third quadrant, then the element will be dissipating power. Okay. However, if the voltage and current VI relationship falls in the second or the fourth quadrant, then it will be delivering power. Did that make sense to you?
Uh, yeah, I have to think.
Yeah,
Sorry.
yeah. It's okay. It's okay. I mean, just I'll just write it here. If the VI relation curve falls in the first or third quadrant, then the element dissipates power. If the VI relationship curve was in the third or fourth, sorry, second or fourth quadrant, then the net power, then element delivers net power. Okay.
So it is just about the sign convention, right? If
Yeah.
both are negative, then it is generating basically positive power, and
Yes.
anyone,
No, no, no.
I
If it
mean,
is both, if both are positive, which means it is dissipating power.
yes, yes, both
Yeah.
are, yes.
Yeah. So yeah, good point. So basically, this holds. No, no. This is actually, yeah. This is this with passive sign convention. Okay. So I think that concludes it. So let's go back to week one. So people were asking me to solve a question on average power delivered. Okay. So I think I have covered average power dissipation problem also. I think I have covered in this week also. Week two, I think that should clear your doubt. I would like you to before I solve this, it would be good if you can solve this on your own. The question that was pending in the last week in week one, it will be much better if you could solve this on your own once again. If you try this on your own once again, because today I have solved some questions which will give you some idea of how to go about solving. Can you try this again? This will be a homework for you. So last time I didn't solve this, but today I solved a question on which covered the idea of which covered the concept of passive sign convention and power dissipation also. So I would like you to try this question once again. I will try. If you try this, probably you will be able to understand it much better in the next session. So some people were asking me to solve questions from week one. Is that okay? Or do you want me to solve it now itself?
No, no, we need help. It is, thank you.
You want me to solve it right now, right? Uh, I didn't understand what you mean by need help. Do you want me to solve it right now, or I should give you some time to again try it on your own? This question, which was left in week one, in the last session. Will you try it once again, or should I solve it here? So, no responses means what? Difficult to judge. Okay. Yes, Saki, you want to say something?
Yeah, my concept was to solve this. I think I missed this question actually. The V2 voltage was not there if I
No, no.
in the last week question.
No, no, this is a problem which I made on my own here. Okay.
Oh, okay, 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 okay. Then
Yeah, yeah,
I can try.
yeah. Yeah. You are right. In week one assignment, this V2 voltage was not there. Yes, you are correct. This voltage source V2 was not there in that. So, see, I didn't cover this. I could not get the time to cover the passive sign convention clearly at that time also. But I gave actually an idea of what is passive sign convention, and I could not get the time to uh, do a question on average power dissipated by the elements. What is meant by negative? What is meant by positive? So today, since I have covered that, I would like you to try this once again. And since you also asked me a doubt about what is meant by what is net power dissipation and what is like. So all those things are here. All the things are available here. So I would like you to try once again. Okay, I will definitely, if you're not able to solve this, I will solve this in the next session for sure. But this I would like you to give it a try once again, because now that I've covered it, I think you will be able to solve it. And also the question that was, sorry, not this question that I have given here, left here. This fourth question, I would like you to try it with the value of current. So current IA, small signal current IA, when it is changed to 0.6 milliampere. No, 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 no. That doesn't cut it. No. Let's call it 6 milliamps again. Solve question number 4 if IA is 6 milliamps. Okay. Solve for when IA is 6 milliamps. I will definitely follow up on this in the next session. I will ask you, all those people who have attempted it or not. Okay, so be prepared. This is a very important. Here you will learn a very important concept. So that is why I'm pressing on it. Please solve this on your own, and then you will be able to understand the thing that I will be talking about in the next session very well. Okay. Today's session I will cut it short and I will end it here itself. Okay, because I have some other duties also. Okay, today I will keep it short. I just wanted to solve one problem, because that will, solving this problem diligently will give you an idea of how to attempt all the other questions in the assignment. It will also give you an idea of what is linearization and everything. I hope you understood this. If you have any doubt, you can ask me. Like, you can unmute yourself and you can say something if you have any issues or any doubts. Otherwise, I will just end the session here for today. Next session, I'll try to. I will not cut the next session short. Okay, this session had to be short because I have some other things also. Only for today.
So, sir, for in my I want some clarification
Uh-huh.
about if we are using for small signal equivalent resistance. If we are
Yes.
getting a negative, we have to take it as it is.
Yes,
So
yes.
we should not take the modulus.
No, 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 no. If it is a
So,
negative resistance, means you're getting negative resistance. Yes. Not taking any
so
modulus or anything else.
means it is delivery.
Yeah, yeah, yeah. It is delivering. Yes. So that, as I said, the negative resistance here does not have any physical significance. Okay. It's just
Sure.
that we have made a mathematical model of the element around this point. We have made the mathematical model of the element around this point. Okay. And that mathematical model is saying that it behaves like a resistor, but just as a negative resistor, not as a simple positive resistance that you are familiar with. But this is a negative, it behaves, it manifests itself as a negative resistance, as a in the strict mathematical sense only. Okay, I hope you understood that.
Okay.
Yes. All right, so if there's no other doubts, I will just end the session here. Okay, I will see you again next time. That will be a full 2 hour session, don't worry about that. Okay, thank you.
Thank you, sir.
Thank you.